Last week, we actually connected the response to the input and make a feedback loop, right? This one. This one. We got the signal, the response, the output, and then compared it with a reference. Okay, before this, we didn't have a reference. Before this, we didn't have a reference. Okay, what we had was this one. You have a power source, right? Some external input to the plant, right? The system, and then you determine the output, the response. So that was it. There, we don't call this as a reference. This is the energy source, the driving force of the plant. Okay, what you see over here, it's not exactly or necessarily the input or reference input to the plant. Right? Okay, so every plant has some driving force without any control, without any uh, 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 any intention of what it is supposed to do. So it only says, okay, provide some energy to the system without any regard to what's going to happen, good or bad, right? So that is the energy source, just like any battery that powers a device. Okay, so that is not any intelligent or any device which has a plan, a goal, a coded system, nothing. Okay, and there's no checkpoint. It's just giving power, and there's an outcome based on that. So it is basically uncontrolled driving force of the plant. So we discussed this relationship, the power source of the system and the response. Now we want to put some controls on it. Okay, so this power source is under control now. We brought it under our control. How? We measure the response and compare it with a new signal. It's not a power source. It's what we want the system do. Okay, so that is new signal, reference input. And if there's any difference between the reference input and the response, we know that we have to do something, and that signal we pass to the driving force. So therefore, the driving force is a variable driving force now, not a constant one. Okay, so it changes. It changes in a certain way so that the response becomes equal to the reference input. So this is the basic concept of control systems, where you compare the response with what you really want it to be, right? The reference value. And then any difference between these two, you use it to drive the power source of the plant. Okay, sometimes you increase power, sometimes you decrease power, until you get the reference and the response equal to each other. That is one thing. That is one thing I want to tell you. The second thing is that you want to have some dynamics in the plant, in some dynamics in the plant. Like, for example, like when you go to a doctor, when you don't feel comfortable, right? He suggests some dynamics for you to recover from your illness, right? He could give you some very heavy dose so that you will be recovered in few minutes, let's say. But that is not the dynamic process there. The doctor plan for a week or so, right? And start giving you medication in certain way so that you start feeling better in a certain pattern, not very abruptly, not very quickly. So this is what is called the dynamics. Okay, it's not a very sudden thing, and gradually you recover. You reach the reference point. Okay, gradually within a certain period of time. Control systems are also the same. We don't want very quick corrections of the plants. We sometimes do that, right? But most of the time, we want to optimize something, getting to the reference value as quickly as possible while keeping other subsystems undisturbed. And there are so many other things that we have to think about, right? For example, when you don't feel well, you go to the doctor and he knows what's your problem. But if the medicine is just one pill, let's say. But in addition to giving just one pill, he gives so many pills, right? Maybe three, four, five, six. Actual medicine is one or two pills. The other ones are to control the side effects, okay, of that pill, because the pill is not perfect. So while it is recovering you from the illness, it causes certain other things also. So the doctor has to give you additional medication so that these bad effects are controlled. So very much the same here. When we want the system to the reference, the response to reach a certain reference, right? We have to plan it, how we want to get there. Okay, so everything is like that. You can't have very quick, sudden, jerky things in order to achieve something, right? Then you disturb the whole system, right? And sometimes you may not get there, right? Even though you think it is good. So like we in normal society, we call knee-jerk reactions, right? You think you are better off if you do that way because you can achieve what you want quickly, but it doesn't happen that way. So you have to plan, you have to communicate, right? And you have to figure out where you are, where you want to be, and gradually reach your goals. So that is dynamics, right? So getting to the final goal is one thing, but getting there, right, in a smoother manner without any bad effects is quite another, right? So we have to achieve both simultaneously. So that is why we have to design the systems with some sort of dynamics in it. Okay, right? I think this is very important to understand. So I think we have completed that part. Now, probably today we can start off with uh, the second system, feedback gain in a stabilized platform. This is the second example. We have taken it from from scratch, shock absorber. Now we developed a height stabilized platform, right? So there you can see the actual height of the table is measured, right? YT, and then you compare it with the reference, and this is the reference, okay? And then you get the error to drive this force. Now, this force is not constant. It's not the rider's weight anymore. That is gone, long gone, right? That is shock absorber. Now, this is a stabilized platform. So that this UT you use to control the force, increase it, decrease it in a certain pattern, right? And gradually we expect the table to uh, go to that particular height, RT, and settle there. Right. So if we start the process, right, we know what to do, right? It's very clearly defined. We start with the open loop plant, GS. So what is GS? GS is the relationship between UT and YT. UT and YT. No control loop, just UT and YT. If you give a certain input to the platform, what's going to happen at the output side, YT? Just that. There's no control, there's no planning, there's no coordination, nothing. Okay. And using GS, we know how to determine GCS, that is a closed loop transfer function. That is the relationship between RT and YT. Okay, so GS, this one is UT and YT, and GCS is YT and RT. Okay, so this is the closed loop transfer function where UT goes as an internal variable, right? We don't really care about what force is required to bring the table from where it is to where we want it to be, right? That is all internal signals. There are so many internal signals. It's important signal, but what we really want is to figure out the relationship between RT and YT. Okay, so that when you change your preference, right, the table will follow your reference. Let's say you set it to 1.5 centimeter. In about 20-30 seconds, you get that. The table will go to that level and settle. And then you immediately change the reference to, let's say, 4 centimeters negative. Right? In about 1 minute time, the table will go to -4 centimeters and settle there like that. So whatever required force to do that will be internally decided, right? We want to monitor that signal also, how the force is actually changing. But more than that, we want to figure out how YT follows RT. Okay, so that is the closed loop transfer function. So I think you remember how to get there, right? GS over 1 plus KGS, remember? So you put that there. This is GS, this one, GS over 1 plus K times GS. So once you simplify this, it becomes like this. And then all of a sudden you tend to see this as another open loop transfer function where you have RS on the left hand side, YS on the right hand side is one block. And you might mislead yourself, this is open loop transfer function. No, this is a closed loop transfer function. But after simplifying the rational polynomial, right, it looks like this, an open loop transfer. So that is why I said the other day also, just because you see something similar to an open loop transfer function, there's absolutely no way to judge it and say for sure it is whether it is open loop or not. Okay, because there are internal feedback loops. Now, the takeaway from that point is this denominator polynomial of S. You see this one, denominator polynomial. In any transfer function, open loop or closed loop, right? The denominator polynomial is extremely important because the solutions of the characteristic equation, which is the denominator polynomial equals 0, right? Tell you the nature, the personality, the behavior, the characteristic of the plant, right? Whether the plant is slow, whether the plant is fast, whether the plant is oscillatory, whether the plant is like a piece of rock, right? Or whether the plant is unstable. So all these characteristics are embedded in the solutions of the characteristic equation, which is the denominator polynomial equals 0. And that is why it is called characteristic equation. It's like the character certificate, right? Everyone has a, you can say, horoscope or character certificate, right? It's what you are, who you are, right? Your personality. So very much so. Here you have a signature polynomial here. When you set it to 0, you can find out the solutions for S. If it's a quadratic equation, you have 2 solutions. Just looking at the 2 solutions, you can tell a lot about the plant. So in this particular case, the 2 solutions, let us call it S1, S2, are given by this equation. You know how to solve a quadratic equation. And then you get the plus or minus square root this thing. So if the square root here, this is what is called the determinant. If it is positive, you have two roots, plus or minus, both are real, and you have two real roots, real, right? But if the determinant is negative, you have a negative square root or square root of a negative value. Then what you have is complex numbers. We call it a pair of complex conjugate pools. And if the determinant is zero, both poles are on top of each other, coincident poles. Okay. And if the square root of the determinant is exactly equal to this number here, right, sigma, then what you see is one of these roots is at origin 0, because minus sigma plus sigma minus sigma minus sigma. So one pole is minus 2 sigma, the other pole is 0, right at the origin of the plane. So what we call this rigid body dynamics. Last week is for that. Then it doesn't have any dynamics. It's very, very rigid system. So all these possibilities are there, and exactly what kind of response are we going to get out of the plant is determined by K. Okay, so because all the other things are system parameters, sigma, rho, and eta, right? They are coming from the plant. The spring constant K is here, the damper coefficient B is here, the mass here M, they're all there, right? You can't change it, right, at will. Once you design it, they're there. So only variable is K. So the interesting point is that now we have one single parameter here, right? It's not a physical thing like the spring and the damper, right? It's pretty much a programmable gain, right? So you can adjust it electronically. So all of a sudden you are in control, right? You can make the system unstable. You can make the system critically damped. You can make the system oscillatory. You can make anything, right? So by changing K. So now we explain, right, all these possibilities in one single slide here, right? If the square root determinant is sigma equal to the real part, just to the left of that, right, minus sigma, then one of the poles is at the origin, right? So one pole is located at the origin. So at that time, if you look at this equation, you can calculate K. At what value of K are we going to achieve this one? So the answer is sigma over rho over eta, negative. And we give it a name Ku because it's a specific value of K, ultimate gain. Right? Because if you change it from there, actually, if you reduce the gain below that point, you are unstable. And when the determinant is 0, right, then you know this part is 0. So the two poles are on top of each other. We call it critically damped condition, critically damped response. So what value of K would do that? So you can calculate that using this equation. So Kc is equal to this one, sigma square minus rho over eta. Okay, you just need to set the gain to this value if you want to have a critically damped system. By the way, I can tell you what really means it to say critically damped system. When the system is critically damped, right, as usually it is the minimum energy system. In engineering, we care about energy, right? So you want to reduce the energy, you have to critically damp the system. If it doesn't cause any other problems, right? If the response is not seriously affected, you better go for critically damped conditions. Then if K is below Ku, this one, right, negative, is going down. The system is unstable because the pole, which is at the origin, now cross over to the other half, the positive half of the S-plane. Then the system is unstable. When K is between Kc and Ku, between these two, right, the system has two distinct real poles, right? So we saw this earlier. When the system has two distinct real poles, system is overdamped, right? System is overdamped. Overdamped means you make it overly slow. System is slow, just like our government institutions, right? It's very hard to make a move right through the system. So overdamped. Now, when K equals Kc, critically damped system is somewhat faster. There's no delays, kind of efficient, right? Like our private sector maybe, right? And then if you increase K further from Kc, system becomes oscillatory, but it goes beyond what you really want and then come back, a rebound, and then goes up again. So it goes up and down, oscillations, and it settles at the right place. So this is somewhat not appreciated because of this too much of a dance, right? Going up and down around the reference. But there are good things also because you quickly get to the reference value. The problem is you don't stop there. You go past that and then come back. So unnecessary movement sometimes. So therefore, it's not the most energy efficient way of doing things. You have seen people like that, right? Uh, overly active, but they achieve so many things, right? But sometimes hurt somebody, right? But things are happening, not very efficient, not very peaceful. So many um, actions, right? So it's a bit of everything together. So that kind of systems are also there, oscillatory systems. But they are stable, sometimes good, right? So all these behaviors can be realized using K. So if I put all these possibilities into the pole plane, this is what is called pole plane. This is a real axis. This is imaginary axis. This is the origin, right? And when K equals 0, when there's no feedback, right? There's no feedback. The system is like this, let's say. And if you reduce K, right? K less than Ku, this pole goes this way, this pole goes that way. So they start moving from their respective positions from here this way. When you reduce the gain from 0, right? Let's say when you don't have any feedback, K is 0. Now you have two directions to go, positive K, negative K. So let's say if you start the negative direction, right? This pole goes that way. This pole goes that way. Negative K, all negative, okay? And at some point, some negative value, this pole is at the origin. So the system is uh, rigid body, okay? And if you reduce K further, you enter into the positive half plane, right? The exponent becomes positive, which means it is exponentially increasing. So it's an unstable system. Now, if you think about the gain from 0, you increase to positive, right? Then this pole moves leftward and this pole moves rightward. They are head on now. They're moving head on, right? Like a collision. and at some k, they meet each other here, and that is Kc, critically damped value, Kc. You can calculate these values, and if you further increase k, one of these poles go up, the other one goes down. This goes to infinity, positive, this goes to negative. Understand? So now you can tell me what you want to do. If you want to critically damp the system, you calculate the gain for that, right? Here, Kc, and electronically set it, then you have critically damped system. But if you want some amount of oscillation, right, increase the gain further so that you get one pole here, the other pole here, like that. But if you want to slow down the system little too much, right, you set your poles here and here. So sometimes you can go to negative values also, here and here. If you want to make the system like a rigid body, you set K to KU and you get your one of the poles here. So all these things are possible. Right. Any questions so far? No questions? All right, let's move forward. Now, there are many important signals in the feedback control system, like the reference, the response, and also in the middle, the control signal, control input. It's also important to monitor what's happening in the controller. Okay, it's like when the boss issues the command to a subordinate, right? The boss needs to know whether the subordinate is able to deliver it. Okay, if the boss knows that this subordinate is not capable of delivering this one, right? That the boss should not have given those targets to the subordinates, right? It's a pretty common thing. So something like that. If you know that the controller, the actuator of the plant, right, it has its own limits. So therefore, when we set the reference, right, we need to know whether the controller can actually handle, implement uh, the orders, right, coming from the reference. So if I pedal back, it's over here now, UT, right? We are issuing commands. It's somewhat easy to issue the commands, but it's difficult to implement it, right? Therefore, we need to keep an eye on the actuator. Every plant has an actuator. Okay, every plant has an actuator. So the actuator gets commands, varying commands, right? In a dynamic situation, right? When the signals loop around it, and every loop there is a command coming to the UT, right? So it's important to know what are these commands. Then we can judge whether the controller can handle that. If not, you have to replace the controller with the capability of delivering that. Okay, maybe speed, maybe the dynamic range, whatever it is, maybe the resolution, right? You have to pick up the proper actuator to get the response that you need. All right. So I think you will see there's a lot of resonance here in the control systems with your normal life, right? When you are, let's say, a chief engineer, you have so many technical officers around you, right? You give them certain tasks, and sometimes you feel that some of these people are not performing, right? So why is it, right? You have to figure it out, whether the person is overloaded, whether he's incapable of performing what you ask him to do. Then you have to replace him, right? Good for you, good for him, good for everybody. So like that. So make sure whether the actuator is able to deliver. Okay, so for that, what we do is we change the control system slightly. So this time, this is the same control system, but the GS, which is actually the open loop plant earlier. So I have taken it, push it through, and I have taken the response like this. So the signal which is coming out of the summing point, I have extended as the response, right? And therefore, all the blocks after that point will have to go to the feedback. So this is not what we physically do, right? This is for us to create the signal of interest, which is the control signal or control input ut as our response, so that we can monitor it. Okay, to monitor it. So we do all these things before we actually build the system, right? If you have the system already, you can just measure it, right? But this is design phase, verification phase. So there's nothing out there in reality. So we have to do everything on paper, on the computer. So we get the signal, which is actually the difference between RS and the response. And that signal is now, it looks like the response. And therefore, any other block beyond that point will have to go to the feedback. So it's a new system now. Now you can find out the transfer function between US and RS, US and RS. So how does the control signal changes when you change the reference? So you can still use the feedback, the closed loop transfer function, that is GS over 1 plus KGS here, right? So the GS here is 1 because this is the forward loop, right? GS over 1 time over 1 plus KGHS. Remember, actually it is, if I pedal back, right, to show you the feedback closed loop transfer function here, right? So this is the feedback loop, right? GS over 1 plus KGS. Now, if you take, in addition to K, the sensor also, HS, what would it be look like, right? If you look at this equation, YS, which is here, equals RS minus KHS, right? YS. Now this is just KYS, but HS will go in here together with K, right? At that point. Because we assumed HS to be 1, it is not there. Otherwise, it should have been KHS and YS after that. Okay. This is the whole signal now times GS. So only difference is that this K together with K, you get H. Any transfer function on the feedback loop comes with K. So right, so this transfer function comes with K now, so it will be 1, the forward open loop transfer function, 1 over 1 plus K times this thing. Okay, now once you simplify it, it becomes like this. This is the transfer function we use to monitor US, how the controller is performing. Okay, And it's interesting to note that this system also has the same characteristic equation: s square plus 2 sigma s plus rho plus k eta equals 0. Right? Earlier, this one, you had the same characteristic equation. Okay. Now you have changed your response from actual response ys to us, and you get this one. It's the same characteristic equation. So that is another thing you need to remember. When you have a plant, you have its the genuine response over reference, feedback, or closed loop transfer function. Now you can twist, stretch, and do whatever you want to the control block diagram like this, and pull various signals to the response. Right? You change your system to monitor the control signal, to monitor some sensor signal, whatever it is, you can do that. Then it becomes different closed loop transfer function. But if it is the same system that you are twisting, pulling, pushing, whatever, your characteristic equation will remain unchanged. Like here, same characteristic equation. So that is why it is again called, I'm reiterating, the characteristic equation. For a given system, there's only one. Okay, like when you take when you change your reference, say response to control signal or to another sensor signal, the characteristic equation is not going to change. Okay. Right. Now we go to simulation and to see some of the signals, right? Because that is extremely important to visualize and then appreciate it, and then also see whether something interesting. So this is my code. M is 50, B damper, the spring, and the gain. This dg is actually the gain difference, right? Sigma, rho, and eta are there. Gc is the critical gain, right? Gu is the ultimate gain. And also remember the DC gain. So every system has a DC gain, right? That is what percentage of the input, right, is actually coming to the response. If the 100% is there, then DC gain is 1. If the 50% is there, then the DC gain is half. So that is also an important thing to know. So then I have subplots 211 here, right? There are different gains, GC plus DG, which is to say that you set your gain from your critical gain plus DG. And here you set your gain to critical gain. So you will see the critical behavior, critically damped behavior, right? Then here you have GC plus GU by half. So this is when you set your gain in between GC and GU, critical gain and ultimate gain. So in between. So you will see an overdamped behavior. Okay. So like that. This is G equals 0, no gain. So then you have the open loop transfer function. Okay. Like that. Then this is the control input. Right, previous one is the response, now it's the control input. How control input is changing in all these same cases. Okay. Gain is set to various values, which are actually the same values over here on this list, but this time you monitor the control signal. Okay. And finally you visualize it like that. So take a good look at it. And this gamma here, I'm sorry about these symbols. Gamma is actually the gain. right? So what do you see? So you see here the table height, which is the response for a unit step, okay? So the step is 1, that is 1 centimeter. The command is 1 centimeter, right? The platform has to go down by 1 centimeter from 0 and settle there. So this is what happens for various gains that you set. When the gain is critical, gamma C, you get this response, the green color, and this is how the force changes. Initially, there's some force, and gradually it goes down and settles somewhere there. And keep that force. Now, if you set the gain between critical gain and ultimate gain like this, so divide by 2 means right in between these two, right? You get your response like this. It's somewhat slow, right? If you see the critically damped case here, it reaches whatever it reaches eventually, right? Like in 1 second, like in 1 second. Whereas the slow system, overdamped system, it takes a long time. Somewhere here, at 2.5 seconds to settle. Now, settle means not the accurate response. It settles somewhere with an offset, with an error. But at least it settled down. That is good news, right? So this overdamped one, it settles somewhere here, 0.8, 10 to the minus 3. It's not actually what we want, but it settled down, right, in about 2.5 seconds. And the third response here, gamma plus gamma equals gamma C plus 6,000, which means bit higher gain, higher than the critical gain. So we know system has two poles, a pair of complex conjugate poles. So the response is oscillatory. You can see this oscillation here, small oscillation. And if you look at the control signal, you see a big response here, right? So this is how the control input goes through this oscillation. Yeah.
Hello, sir.
All right. So this is it. Uh, uh, Right. Any questions? Right. So if there are no questions, right, uh, we can now think about the adjustment of the response, right? Adjustment of the response. Because as you saw in the previous slide, the response is not actually big enough, but that is a separate thing. Okay, that's a separate thing. Once we decided, okay, we want to have a critically damped system or a slight oscillation or over damped, right? We have to first get that shape, the nature of the response. And after that, you can amplify it by a factor of 2, 3, 4, half, whatever, by adjusting the DC gain. Understand? So, if we create a problem here, a design problem, like this, for example, we want to design a critically damped system, right? So if you calculate what is the critical gain here, it is like 2325. So when you have 2325 as the gain, you can calculate what is the DC gain of the closed loop plant, because the DC gain is this, eta over rho plus critical gain times eta. So we put all these numbers here, right? This is the critically damped condition. The answer is 4 in 10 to the minus 4. Okay. So now you know that your gain is very, very small, but it is the critically damped condition. Now, in order to bring the response to real magnitude, what you want to do is get the reciprocal of the existing DC gain of the plant. So which is 1 over DC gain, that is about 2150. And use this gain like here, right? So rather than asking just the unit magnitude, right, as the input, now we ask 2450 times, because we know that we are going to get 1 out of 2450 as the response. Understand? So we are not going to boost the response up, but in addition, we ask that much stronger, big input from the input side, knowing that the system is going to give you a very, very small fraction of that. So, but what really wants, what we really want here is to get the response to the unit magnitude. Okay. So whatever you want to do, you have to do, right? For that, you can have this pre-gain calculated, right? So this is like deceiving the plant. We are deceiving the plant saying that we want 2150 centimeter change, right? But we know what is happening. The system is going to give us 1 out of 2450, whatever you ask. So it will give us 1 centimeter. So 1 centimeter is the actual need here. Right. So these are the things that we do in control systems. Okay. So with that, we get the response like this. Table height in centimeters, right? It goes like that. Critically damped, very nice. No overshoot. Fast enough, less than a second, it gets there, right? When doing that, the force exerted by the actuator starts somewhere here, goes like that. So that's it for the single gain feedback control, right? This is very basic uh, uh, control system theory and practice, right? But I think it showed you the essential basics, the concepts, right, in designing a feedback loop. Please ask any questions if you have up to now.
Hello, sir.
Yes, go ahead.
The previous slide, we are going to add some gain for unity, making unity. The required gain
Say it clearly. I can't hear properly.
for design for the unit, the gain.
Yeah.
So we are calculating and we are going to add with the KC, right? Already existent gain.
We are actually doing two things. One is adjusting KC, and after that we adjust the DC gain. Two steps. Which one are you referring to?
That required gain we are going to add.
No, no, here required gain. So this is the DC gain adjustment. This is the second part of the design. First part is to critically damp the condition, the system. To critically damp the system, we adjust this one. To critically damp the system, we adjust this gain. Okay, and after that, we put another gain over here to adjust DC gain to unity. Right. Please ask, what exactly is your problem?
That one I asked. The DC gain we adjust for the unity critical damage.
Say it again. Say it again.
That DC gain
Yeah.
we use it for the unity of critical damage.
No, no. Now, when you set KC to 2325, system is critically damped. Okay,
Okay.
the system is critically damped, and on top of that, okay, if you want to have unity DC gain, you need to have additional DC gain here, additional gain here, free gain, and that is 2450.
Okay.
So this one will make the system critically damped, and this one will make the plant unity DC gain.
Okay. That also will come to feedback. Right?
No, it's not a feedback, because
Okay.
this is not a gain in the feedback, right?
Uh, okay.
Feedback is from here. So look at that, how the signals go, like that. This is how the signals move, right? This is remaining unchanged.
Okay.
Any other questions? All right. Then we will start the next uh, Right. So let us start this one. Root locus design. Don't worry about this number 5. Okay. Now we are going to put this feedback gain, use it as a standard control system design criterion. Okay. Because earlier we just tentatively used this gain, right? Out of curiosity, intuition, we just put a gain there and see how it works, and we know it really works, okay, that way. So the essential fundamental thing for feedback control or better control is that to get the response, feed it back through a gain, right? So already we saw some good results. Now I have some messages here. It's heavily draining some areas. Yeah, so please turn off your router, and it's okay to leave the lecture now. If you are in danger of getting your routers and computers burned, right, of lightning, the lecture is being recorded. You can listen to that later. And if you have questions, you can ask me. That's perfectly fine.
Sir, the recorded lecture where it's get uploaded.
I think some of the lectures I uploaded. When I upload it, Damit said automatically message goes to the students. And I also got some of these messages by email, right? I uploaded about 2 videos, if I remember correctly. If you haven't got it, talk to Damit. Maybe your email address is not there in the Moodle, right? Otherwise, the moment I upload uh, a lecture or any material, a video, right, to the Moodle course Moodle,
Okay.
you get a email immediately. Then you can, through the link, you can download the video, the lecture slides, everything.
Sorry, sir. It's in the announcement section, I found.
Say it again.
It's in the announcement section. I found it. Thank you.
Yes, that's right. All right.
Excuse sir.
Yes, go ahead.
So only first 2 lectures are uploaded. Last two lectures are not uploaded, I think.
Yeah. I'll do that. Sometimes I cannot punctually upload every week just after the lecture. Sometimes delays in my side because I'm handling so many things at once. So I'll definitely do that in a batch. Maybe this week I can do that, right? I will check what is available there. Maybe 2 lectures I know, and some of the videos are not there. Yeah, I'll upload, right? Probably this week I should be able to do that. Right. Okay. Any further questions? Right. So, as I already started telling you, now this is a very elegant feedback control design method using feedback gain. So over here you can see the feedback gain, right? Uh, right? So rather than learning, maybe you can assume exploration kind of mindset here, right? We are going to explore how we can do this kind of controls like the world has never seen before. No control systems in the world, and you are the first people to build a feedback loop, right? So that mindset is very important. So we have already seen that putting a feedback gain over here gives us the leverage, right, to control or dictate the terms in the loop, to make it unstable, even to make it critically damped, oscillatory, um, rigid body motion, everything, right? So that is what is called controlling a plant. So therefore, this has happened more than a half a century ago, right? What we are trying to do today, right? A person by the name Evans, right, actually did a lot of good work and put this feedback gain paradigm into a very elegant criterion for designing feedback loops. So we are going to do just that. Now here you can see a plant, a sensor, and a feedback loop. Okay. Now if you write down the transfer function, this is what you get. We have already done this. Ys is equal to Rs minus k times Hs times Ys. That is the difference multiplied by Gs. Yes. And after that, you bring all this Ys term from right side to the left side, and it will be like this. And after that, you keep Ys here and bring Rs from the right hand side over here. Ys over Rs. So Ys over Rs is equal to this one. This is the feedback or closed loop transfer function. And now you go to the denominator here, that is 1 plus k HSGS. You put that part equals to 0. This is the characteristic equation, right? Characteristic equation. Now, the solutions of this equation, like for what S, you're gonna satisfy this condition. So those S's are the solutions of the characteristic equation, and we give a name to those solutions, roots. Okay, roots. We call them roots, the solutions of S in this equation. Earlier you had the quadratic equation, characteristic equation. So you had two solutions. So two roots. When the two roots are on top of each other, critically damped. When the two roots are actually, they form a pair of conjugate poles, system is oscillatory, like that. And now you know that when you change k, the solutions also change S. For a given k, there is some S1, S2. When you change k, S1 and S2 both change. Now when you have these roots changing their location, as you change k, you can plot them, the position of the roots. Then you get a curve, a line, a path, a locus, basically. Locus, the path. And that is why it is called root locus. So we are going to draw or sketch the root locus of the plant, a feedback control system, as k changes, where the poles are, and as you change the k, the gain here, where are these poles moving? If you have this diagram, with numbers on it for k, now you can tell me if you want to have a critically damped system, what is the value for that K? If you want to have some, say, 10% overshoot or whatever, what is the gain for that? So you just have to go to the controller and set the gain, and all of a sudden you get the critically damped condition or 10% overshoot, whatever. Okay, so that is the purpose of this lecture, to sketch the root locus. Now, to do that, this is my approach here. I take this 1 to the right hand side, it becomes -1, and it is K times Hs times Gs. So your sensor transfer function, you put it over here, your forward loop transfer function, you put it over here, and this is the gain K is equal to -1. So one single equation. Now this equation is about the closed loop transfer function, because you can see this K here, but inside this equation you have GS. GS is the open loop transfer function. Now this is a really interesting case. We analyze the closed loop transfer function but using the open loop transfer function. Understand? This is the open loop transfer function. So we analyze the behavior, the characteristics of the closed loop transfer function using the open loop transfer function. Because open loop transfer function is very easy to handle. Feedback, when you get the loop closed, it becomes a bit complicated. In the reality, in the physical world, we do the connection and everything. But to analyze the plant, we can do almost everything using open loop transfer function. So that is the beauty here. Okay, right. Now if you look at the last line here, what do you see? Hs is the sensor transfer function, Gs is the open loop transfer function, is equal to -1. And these S's, as you know, right, they are the positions in the phase plane or pole plane, right, where you have real axis and imaginary axis. It's a complex number space. So therefore, what you have on the left-hand side is a complex expression in general, because these poles, sometimes they are real, sometimes they are complex. Okay. So the roots, the solutions are actually on the complex plane, right? Where you have real axis and imaginary axis. I think you saw one of these root loci previous lecture, previous in the sense today, just before this one, where you saw K equals 0, K equals Kc, K equals Ku, and the poles move towards each other or away from each other, and then they meet up in the middle, and then one goes north, the other one goes south. So that is what is called the root locus, basically. As you change K, the poles move. So in fact, we have done one root locus already, but you did it in a cut and dry manner, not a methodical, mathematical manner. So now we are going to figure out what are the rules here, how we can draw a root locus, right, systematically. Now, remember this equation, KGSHS equals 1, because this is extremely important going forward. Now, when you have this complex expression, KHSGS equals -1, right, -1. So I can draw it over here using pen, right? This is the imaginary axis, this is the real axis, this is -1 somewhere over here, right? So let me put some mark here. So this is -1, right? This is -1. So on the left hand side, there's some expression. So this is real axis. This is real axis. This is imaginary axis. Okay. So when you say -1, right, it is this complex number from 0. It is this complex number. So if I want, I can put an arrow here, right, to, sorry about that. So like this. So this is -1. This is -1. So as a complex number, it's a bit different than simply saying -1. Okay, simply saying -1 because it has magnitude and phase. Magnitude and phase. So magnitude of this is 1. The magnitude is 1. Phase is this one. This is the phase. So it is 180 degrees. Right? So this is 180 degrees phase. So it is magnitude 1, 180 degrees phase. So 180 can be plus or minus. So that is how we treat complex numbers. Okay, right. So we'll move forward with that. So on the left hand side then, we need to understand that this whole thing, if you look at the magnitude, it is 1. If you look at the phase, it is plus or minus 180 degrees. So that is, these are the two conditions of root locus. The first condition is that the magnitude of this has to be 1. The second condition is that the phase of this has to be plus or minus 180 degrees, because this is equal to -1. When you say minus and it is 1, the magnitude is 1, just because it is minus, right, a real number minus some real number. So the phase is 100 degrees. Clear? So if it was like +1, if it was +1, what is the magnitude? What is the phase? Very simple question. If it was magnitude
1,
1,
phase 0.
phase 0. That's right. So because it is on the other side, phase 0, right? This is very basic, but it is important to refresh yourself because you are coming maybe even without touching any complex numbers for a long time. So you might have forgotten these complex numbers, right? So let me therefore just recap some of the things, because otherwise this will be very painful for you to understand, right? So if I pick up a number here, right, a complex number, right, or maybe somewhere here, some clear area where this line over here is maybe A, and if you get to this part, maybe it is B. It is actually JB, right? So the complex number here is complex number here is A plus JB. right? A plus JB. So what is the magnitude? A plus JB. So A plus JB. So this is the complex number. Let's say this is S1. What is the magnitude of S1? We write it like this, S1 magnitude. And what is the phase of S1? We write it like that. So what is the magnitude?
Square root of a square plus b square.
Say it again.
Square root of a square plus b square.
Yeah, that's right. So the magnitude is this one from here to here. So this line, get the magnitude. A square plus b square. I think you know that, right? And then get the square root. Fine. And what is the phase? What is the phase?
B over A.
BOA.
Tan inverse B over
Okay, we can say,
180 minus tan
yeah,
inverse
that's
B over
right.
A.
That's right. So you can say 180 minus tan inverse B over A, right? So like that. So that's good enough. I think now you can follow, right, what I'm going to do here. All right, interesting. Now here, up here, you can see the magnitude and phase conditions. I have already explained. The first one here is the magnitude is equal to 1. Second is the phase condition, which is equal to plus or minus 180 degrees. So when I say 180 degrees, I can, if I want to be mathematically perfect, I should write it like this, 2k plus 1, where k equals 0, 1, 2, etc., right? All the integers following up. So just to be mathematically perfect, right? But what essentially is happening is plus or minus 180. Right. So let's take a little break here, right? About 10-15 minutes and start over again, right? Okay. Let's start from here. Now, the two conditions are very clear, right? So keep that in mind. You can sketch these conditions on your notes, right? Now, our focus is entirely on these two conditions, right? The first condition is relatively easy to remember. The magnitude, you know how to calculate the magnitude of a complex number, as you said, uh, square root of the square sum of real number and imaginary part. Okay, real part and imaginary part. So that's it. The phase condition can be a bit complicated because if you look at this expression K, HS, GS, now HS is a transfer function. It is the sensor transfer function. GS is the open loop transfer function. So if you look at these transfer functions, right, you have seen before, they are rational polynomials of S, like this, rational polynomials of S. So it is a polynomial of S in the numerator divided by, right, another polynomial of S as the denominator. So both of these are like that, HS and GS. So when you combine them together, multiply them together, you generate something like this. Okay. So you break it down to first order terms. Now, if you look at the numerator, maybe it's a third order polynomial of s. And you can break it down to 3 of these first order blocks. And if the denominator is fifth order polynomial of s, then you can break it down to 5 of these first order blocks. If the denominator is fifth order, it has 5 poles. 5 poles, right? And if the numerator is broken down to maybe 3 first order terms, and each one like this, right? You have solutions and we call them zeros. S minus Z1 is equal to 0, S equals Z1. So Z1 is a 0. So is Z2. Z2 is another 0. M is another 0. Okay. And P1, P2, Pm are poles. So as you know, we draw the zeros like this, right? With a bubble like this, and these poles like this one, and this one, right? With a cross, right? These are the zeros, the poles. Okay, so now when you have this expression and saying that it is let me first erase these things and right. Right. So now if you focus on this one, it is a complex expression with individual blocks, first order blocks here, with these zeros and this numerator or denominator polynomial broken down to first order terms again, with the P1, P2, Pn as poles, right? The whole expression has plus or minus 180 degree phase. Right, this is the condition. So whatever is that satisfy this condition, right? If you look at these poles, we are referring to these poles, right? And also for zeros, right? These are fixed things. Now if you break this down to polynomial like this, you know what Z1 is, Z2, Zm. You know P1, P2, Pn. You know these numbers. Okay, you know these numbers. Then when k comes in, right, k is not going to have any phase because k is a real number. K is a real number. So therefore, the entire phase here is determined by this S. By this S. You can put different S values and see for yourself, right, whether it satisfies this phase condition. If it is the case, that S is on the root locus. If a certain S does not satisfy this condition, phase condition, that S is not on the root locus. So that is the one thing you need to remember going forward. Okay, so what is that S that satisfy this first condition? You can substitute different values for its origin, imaginary number, a real number, or a complex number. Just substitute on this equation and see for yourself what is the phase you get. If the phase is 180 degrees, so there can be an infinite number of S's that satisfy this condition, and an infinite number of points for S. Some points are real, some points are imaginary on the imaginary axis. Some points are complex, combination of real and imaginary, right? And all these numbers that satisfy this condition, the total phase is 180 degrees, then those points are on the root locus. That is what we say, on the root locus. So if you have these points and put them on the plane and join them, right, you will generate the path, the curve, and that is the root locus. Okay. Now, if you break this down further, how do you calculate the phase of a rational polynomial of S like this? Rational polynomial means actually two polynomials, right? Numerator and denominator. Okay. So, and now it is broken down to first order terms. Now you can calculate the phase of each and every term here in the numerator like this. What is the phase of this term? What is the phase of this one? What is the phase of this one? Like that. And deduct the phases of these individual blocks in the denominator. This one, this one, this one, and so on. So this is how you calculate the numerator phases minus the denominator phases is the total phase of the complex expression. K is not there, as I said, because K is a real number, right? K is a real number. And K is positive as well. So therefore, phase is 0. It doesn't come over here. Any questions so far? Okay. So far, so good. So let's move forward. Now, let's take one of these blocks. Say, for example, one of these blocks, S minus Z1, right? And it is positive because it's in the numerator. Then S minus P1 is negative because it's in the denominator, right? So let's take one of these blocks and see how we calculate the phase. S minus Z. So I don't say Z1, Z2, Z3, whatever. It's general general zero of the system, right? S minus Z. So I want to first take a real zero, which means this is the real axis and this is the zero. Okay, so when you break down this polynomial, right? When you break down this polynomial, you get the first order blocks. And let's say for the moment that these are real poles, sometimes there can be complex poles, right? Complex poles. So let's first take a real one, right? So the real one is over here. Now, the S is the variable. S is the one we want to move here and there and see whether it satisfies the phase condition. Because if it satisfies the phase condition, it's on the root locus. So now let's concentrate onto the real axis, right? Because even though there are a lot of space up and down, right, above and below the real axis, let's focus on the real axis first, right? So I can have my S over here to the right of 0 or over here to the left of 0. Okay. So when I have my S over here, now I am talking about not about magnitude, it's about phase. Now when I'm here, S minus Z, S minus Z, this is S, this is Z, S minus Z. Put a number here, S equals 10, Z equals 3. Huh? 10, 3. 10 minus 3 is 7. 7 is somewhere over here. It's a positive number. So what is the phase? 0. Phase is 0. So if you S, which is on the real axis, and to the right of the 0, it's 0 phase. Phase 0. Now let's say on the other hand, S you have selected is on the left of the 0, somewhere here. Right? Now S minus Z is, let's say this is 5 and this is 15, right? 0, this is 15, this is 5. So 5 minus 15 is minus 10. So minus 10 is over here, this direction. So the phase is 180 degrees. Okay. If S is on the left of Z. So this is true. If you have a 0 on the real axis, and if you select any S to the right of that, this small block here, right, has 0 phase. If the selected point S is to the right of the 0, and the phase is minus or plus 180 degrees if the selected point is to the left of 0. So that is one thing we need to remember, right? And then if you look at a pole, right, it's very similar to this structure. Only thing is negative. So therefore, this is positive 180. If it is a pole, it will be negative 180. But what difference does it make, right? It goes to the same point this way or that way. Okay. So therefore, there's no problem dealing with the poles and zeros on the real axis, and also assuming S on the real axis. S on the real axis. So our discussion so far is only on the real axis. Okay. So real axis is extremely important. That is why we take real axis first, and we are not going to take the space above and below real axis, right? Our discussion is entirely on the real axis, because if you figure out whether those points on the real axis satisfy the root locus condition, you know that that those parts on the real axis are also on the root locus. So that is a big thing to know, right? Parts of the root locus, right, on the real axis we can figure out. So then it will be easier to figure out the other parts which are not on the root locus on the real axis, but above or below the real axis. And also I want to tell you one thing: the root locus is symmetric around the real axis. So if you have something above real axis, you have the same thing below real axis. Okay. Now let us take a pair of complex conjugate poles, because this is again very common. Just a while ago, you dealt with pair of complex conjugate poles. Remember, the two poles move head on and meet up at a point, critically damped condition. After that, one goes north, the other goes south, right? Remember that case, pair of complex conjugate poles, right? So similarly, if you look at, so now that is an interesting point. When the two poles met on the real axis at some point, and after that one goes north, one goes south. So there you can see the root locus is symmetric. Okay, if you have something above the real axis, you have the same thing below the real axis as well, right? Because of this complex conjugate nature of the poles. Now, therefore, it is important to know the phase contribution by pair of conjugate poles and zeros. So I will just arbitrarily take poles, complex conjugate pair of poles. So it will look like this: S minus A plus JB. It is one of the conjugate pair. The other one is S minus A minus JB. And see, this is one pole of the conjugate pair. This is the other one. So it always comes with S minus, S minus. And they are both in the denominator. Okay, like here, like here. And they appear like as pairs. So therefore, when we talk about phase, we have to take them together. We have to take them together. Now, I want to draw this. I want to draw this to figure out the phase contribution. Let's say this is one of the poles, right? A plus JB. This is A minus JB. This is the pair of poles. And we have S, the variable point, whether we want to check whether this point S satisfies the phase condition. Okay. Now, what is the phase generated by these two poles, right? When the S is on the real axis. As I said to you, S can be anywhere, right? But for the moment, we take only the real axis, so which is from here to here along this axis. So first, I take S greater than A. A is the real part of the poles, right? Of the pair of poles, A. So I take S greater than A to the right of A, somewhere here. So this is my point S, right? These are the two poles. Now, if you look at my expression, it is S minus A, the real part, plus JB. S minus A, the real part, minus JB. So when I say S minus the pole, the real part is going to change. So therefore, right, in this scenario, if I say S minus A, right, S minus A is a positive number because S is to the right of A. So I will have a small positive number here, S minus A, positive, right? And this plus JB becomes minus JB. It will come over here because I deduct S minus this whole thing. So therefore, this becomes minus A, this becomes minus JB. So when the imaginary part becomes minus, it comes over here. And real part now is smaller. Now this appears over here. Now this is the S minus A minus JB complex number. So what is the phase of that? The phase is 360 degrees minus theta. Theta, you know how to calculate theta. Now let me take the other one, S minus this pole. So I'm taking a pair of conjugate poles. And S minus this, I calculate the phase. S minus this, I have to calculate that phase. So when I say S minus A, again like before, it is a small positive number. And this minus JB becomes plus JB. So it goes to the upper half, positive half of the plane. So it's over here. And the phase is theta. Phase is theta. So therefore, if my S is to the right of A on the real axis, right, this pole generates a phase 360 degrees minus theta, whereas this pole of the pair generates theta. So 360 degrees minus theta plus theta. What is it? What is it? 360 degrees minus theta plus theta. They are both negative because of the negative sign. The answer is minus 360 degrees. So when I say minus 360 degrees, it is equal to say there's no phase contribution on the real axis. It is same as saying there is no phase contribution on the real axis when the point is to the right of the real part of the conjugate pair. So now let's say if it is not the case, if I have selected a point S to the left of the real part of the conjugate pair, that is A, something like this, what will happen? So again, I have to say S minus this and S minus this, okay, and get the phase. So when I say S minus this one, S minus A, right, S is a negative number. A is also a negative number, right? So I am leaving with small negative number, S minus A, something like this. Okay. So this pole comes over here. This pole goes over there. And this is the new complex numbers, right, from the two poles. So what is the phase of this one? It is 180 degrees plus theta. What is the phase of this one? 180 degrees minus theta. So one is 180 plus theta. The other one is 180 minus theta. So like this, 180 plus theta, 180 minus theta. So when you add them together, it is again minus 360 degrees. So if you move on the real axis from plus infinity to minus infinity at any point, right? If you have a complex pair of poles or zeros for that matter, okay, there is no phase contribution. There is no phase contribution from any of these poles or zeros. So therefore, when it comes to the phase calculation, you can neglect complex conjugate pairs. Like over here, if you have complex conjugate pairs, don't worry. Don't take them into your phase calculations. Any questions up to now? Right. So therefore, we are now going to create the rules, root locus rules. The first one, root locus is on the real axis to the left of an odd number of poles or zeros. Is that clear? Is that clear? Is that clear? Now, so I'm going to draw a line. This is the real axis. This is the imaginary axis, right? So, first of all, I will get say a couple of zeros like this, okay, and a pole also like this, and another pole like this, right? So then I have my point here, right? Which is I would say this is my point S. This is my point S. So I'm going to move my point leftward, right? And as I move along the line, I want to calculate the phase, total phase from all of these poles and zeros. And the rule says this: root locus is on the real axis, which means this is actually part of root locus because it satisfies the phase condition, right? To the left of an odd number of poles or zeros. To the left of an odd number of poles or zeros. So which means if I am here, I am to the left of a pole and a zero. Pole and a zero, which means not an odd number, even number. So therefore the rule says this part, this section of the real axis does not satisfy the phase condition. So therefore this is not part of the root locus. When I jump over here, now I am to the left of two zeros and one pole, which means 2 and 1, 3. It's an odd number. So when I am to the left of an odd number of poles or zeros, it says it satisfies the root locus condition, phase condition. So therefore this part is on the root locus. And if I cross over to that side again, I am to the left of two poles and two zeros. That is 2 and 2, 4, even number. So therefore this part does not satisfy the phase condition. Therefore root locus is not on the real axis here. It can be above or below, but not on the real axis. So that is what the rule says. Now is it true? So go back and see. Right? If it is a 0, right? We saw that if you are to the right of a 0, phase is 0. If you are to the left of 0, it is 180 degrees. And if you think about poles, when you are to the right of a pole, it's 0. When you are to the left of a pole, it is minus 180 degrees. So that is all what you need to remember. If it is a 0, is it? The phase is either 0 or 180. If it is a pole, the phase is 0 or minus 180. Depending on where you are with respect to the pole or 0. If you are to the right, it is 0. If you are to the left, it is plus 180 or minus 180. So now if I'm here, right, am I to the left of an odd number of poles or zeros? No. So we'll go to the next one. If I'm here between these two, what is the phase due to this pole? What is the phase I am getting due to this pole? Can somebody answer, please?
Negative.
Yeah, negative. How much?
180.
180. Negative 180. What is the phase I'm getting from this 0?
0.
0. What is the phase I'm getting from this 0?
0.
0. What is the phase I'm getting from this pole?
That is
That
one.
also 0.
0. So, all of these poles and zeros to my left generate no phase, 0. And this pole, which is to the right, generate minus 180 degrees. So am I satisfying the phase condition? What is the phase condition? Phase condition is this one. The total phase has to be plus or minus 180 degrees. So am I satisfying the condition? Yes or no? I have two poles and two zeros. 3 of them, they contribute no phase. One of them gives me 180 degrees negative. Is it the condition to be satisfied? To be on the root locus? Yes or no?
Yes.
Yes, it is the condition. When the total phase is 180 degrees, plus or minus, right? You are on the root locus. So which means this section is part of the root locus. Which means when you change your gain for some gains, your closed loop poles, right? One pole or two poles, I don't know how many, right? They will actually be here on the real axis. That is what it says. By the way, this pole and this pole, this 0 and this 0, where are they coming from? Where are they coming from? So I go back to this one. Where are these Z1, Z2, Zm, the zeros, and P1, P2, Pn, the poles are coming from? If you don't know, you are just floating in the air without knowing your position. This is a story. It has a start and an end, and all the way, it's a story. You need to know where you are. Where are these zeros and poles coming from?
So the open loop transfer function.
Exactly. That's the answer. From the open loop transfer function. The moment you know, look at the shock absorber. If you know the spring, if you know the damper, if you know the mass, you know the open loop transfer function. You always know it for any system. And you can easily calculate the zeros and poles here. But when you close the loop, and put a gain, and you adjust the gain, do you know where your actual closed loop poles are? No, you don't know. when you have a closed loop transfer function, for a given gain, you get your closed loop poles. And when you change the gain, the closed loop poles change. It's not a fixed point or points on the plane. But the open loop transfer function, the poles and the zeros are fixed. So this Z1, Z2 up to Zm and P1, P2 up to Pn are fixed poles and zeros of the open loop transfer function. They are not the poles of the closed loop transfer function. Understand? So what we are going to look at is, where are these closed loop poles? Okay. So as you change the gain, they move. So we want to figure out where they start from, where they end their journey, and in between at any given k, what is their location? Are they on the real axis? Are they above and below the real axis? Are they at infinity? Are they crossing over to the right half plane? Those are things we need to know. Right. I think you got the point. Now for poles and zeros on the real axis, open loop poles and zeros. The moment you know the open loop transfer function, you can draw them on the real axis, poles and zeros. And now you say, from here to here, this is part of the root locus. Okay, and when you go past this 0 to here, between here and here, right? What is the phase generated? What is the phase generated by this pole? There's a pole to your right. What is the phase generated by that pole?
Negative 1.
Minus 180, right? What is the phase generated by this 0?
Negative 1.
No, it's positive, right? It's positive 180, right? It's a 0. It's a 0, like this. Positive 180. So negative 180, positive 180, 0. Cancel out. So therefore, the phase here is 0. Are you satisfying the phase condition? No. If you satisfy the phase condition, the total phase has to be how much?
180.
180. So therefore, root locus is not here. It's not on the real axis from here to here. It can be somewhere up and down. We don't know, but certainly not here. Then you go past this point over here. Then what happens? Do your calculations and let me know whether from here to here satisfy the phase condition of the root locus.
Plus 180.
Yeah, that's right. So from this pole 0, you get 180. From this one, you get another 180. From this one, you get minus 180. So total is plus 180. So therefore, it satisfies the condition on the root locus. Then you go past over here. All the points from this point onwards to the minus infinity. So do I satisfy the phase condition?
No.
No, because these two poles will generate minus 180 each these two zeros will generate plus 180 each. The total is 0. I'm not satisfying the phase condition. So therefore, I can draw like this. I can draw a thick line here saying that I'm satisfying the root locus phase condition. So this is part of the root locus here and here, right? So there you can see two parts, right? This part and this part is on the root locus, RL. So this way I can actually mark sections of the root locus on the real axis. Okay, so that is something really important to know, and that is what is called the rule 1. So let's look at rule 2. Root locus starts from open loop poles and approach open loop zeros or infinity as k goes to infinity. So k is the feedback gain. As you know, when the gain is 0, there is no closed loop plant. There is no closed loop plant when k is 0. K is here. Then what you have is only GS, open loop. So the poles we are having in this situation are open loop poles, right? It is very, very clear. So this is where we start our journey. Our starting point is open loop plant when k is 0. Our starting point is k0. And then we increase k. Our final point is k infinity. So when we do that, poles move from their start point to their final point. So this rule says this: the closed loop poles start from open loop poles. So that part is pretty obvious. When k equals 0, there is no closed loop plant. It's only the open loop plant. And the poles are the open loop poles. Okay, fine. When you increase k, what will happen? Let's see. Now the poles are moving. We want to find out where they are going. Now here on this diagram, you can see this is an open loop pole. So is this one, right? Open loop poles, this and this. So this is when k equals 0. So this is when k equals 0. So I can say k equals 0, right? This one and this one. Okay. So exactly as the rule says, root locus starts from open loop poles, right? From here and here. It further says, and approach open loop zeros. That is very interesting. So see, this particular pole which starts over here moves along the real axis and stop at this point, 0. So this is exactly what the rule says, and approach open loop zeros. And this one in the same time, it moves this way and end up over here when k equals infinity. So I can write like this, for example, this one and this one. Right, this is k equals, k goes to infinity. Okay. Right. So now this is just a intuitive diagram, right? You have 2 poles and 2 zeros, right? These 2 poles are the starting points of the root locus, and these 2 zeros are the end points of the root locus. Start point is when k equals 0, right? When k equals 0, this is the start. This is k goes to infinity. This is the end point. And in this particular case, entire root locus is what you already have here. 2 small segments. Now, if I write this, k goes to 0, right? When there is no feedback, k equals 0, closed loop transfer function is equal to open loop transfer function. So you have a numerator and the denominator for GS. They are both polynomials of S, and you have this open loop poles. You solve this denominator polynomial equal to 0 and calculate the solutions, and these are the poles. So they are open loop poles. Okay, fine. And when k goes to infinity, it's interesting. K goes to infinity. If you write it down over here, now if you have very high value for k here, right, very high value for k here, so ys times hs times very high value, it goes over here, and r is minus a very high value, very big value, and that is the signal coming to gs. Okay, so I can safely say this: rs minus kys, rs minus k times ys. Let's forget about hs, right? K is very, very big. So therefore, this part becomes insignificant. This rs is not significant here when k is very big. So we can say that this whole thing approaches minus ks, sorry, kys. Okay. So there is no rs part here. There is no rs part here, right? So you have k times ys, and it is negative. We multiply with gs, and the result is equal to ys. Like this: k times ys gs is equal to ys. So follow the signal path: k times ys this is not significant, it's negative, multiply with GS is equal to YS. This is the situation you are in when K is very, very big. All right. This is the condition you are in when K is very, very big, which brings you to this condition. So you remove YS from both sides. It is K times GS is equal to 1. And if you isolate K here, it is 1 over GS on the other side. So it goes upside down. It flips over. So denominator goes to numerator, numerator goes to denominator. Understand? And K is very big. K very big means the denominator is 0, which is ns equals 0. So either ns has to be 0 or ds has to be infinity. ds has to be infinity. So ds is actually the poles, ns is actually the zeros. So you are actually reaching the zeros, like over here. You are reaching the zeros, or you are going to infinity. You are going to infinity. So it's pretty clear now. If you have two zeros and two poles in the open loop transfer function, these two poles, right, move towards the zeros and end up there. That's it. Very simple. But let's say you have three poles and two zeros. Three poles and two zeros. Then what will happen is that two of the poles or two of the three poles will move towards the zeros and end up there, and the remaining pole will go to infinity. So when a pole goes to infinity, it goes sometimes along the main axis, real axis, okay, to positive infinity or negative infinity. Sometimes if it is two poles going to infinity, it goes up and down. Sometimes it goes at an angle, 45 degrees, 60 degrees, like that. Okay, and these straight lines, where they finally achieve, they actually go through a curved line above and below the real axis, and gradually this curvature reduces and it becomes a straight line as it approaches infinity. And that straight line, if you extend it back to the main part of the plane, we call it asymptotes. We call it asymptotes. So therefore, if you have three poles and two zeros in your open loop, you have one pole going to infinity. So therefore, you have one asymptote. Now let's say you have 5 poles and 3 zeros in the open loop transfer function. So 5 poles and 2 zeros, right? Or 3 zeros. So then 3 of the 5 poles will reach the 3 zeros and settle there, and other 2 poles will go to infinity along 2 asymptotes. along two asymptotes. So asymptotes are like straight lines, right? Straight lines, like for example, like this and like that. So the poles, they go like that and infinity like that. So the other pole goes like that to infinity. Okay. Right. So gradually you will see that the different parts of the root locus is now actually becoming visible to you. Okay. Rule 3, root locus asymptotes. Now we just started this discussion, asymptotes. When you say asymptotes, you want to know what is the angle of the asymptote, right? Is it on the real axis? Is it on the imaginary axis? Is it at an angle to the real axis? So you want to know the angle. And also, if you have number of asymptotes, okay, they intersect at one point on the real axis, one point on the real axis. That is the point of intersection. So for these asymptotes, I give you these two equations without proof, right? Proof you can find on undergrad control system books. Asymptote intersection point is determined by this equation, alpha. Asymptote intersection point. It's on the real axis. It's on the real axis. What you do is this. You add all the open loop poles minus all the open loop zeros, divide by n minus m. N is number of poles, m is number of zeros. So as I said to you, if you have 5 poles open loop and 3 zeros open loop, 5 minus 3 is 2. You have 2 asymptotes. Okay, you have 2 asymptotes. And this equation tells you asymptote intersection point. At what point on the real axis these two asymptotes meet up or intersect. And then angle, asymptote angle. What is the angle between the asymptote and the real axis? It is given by this equation, 180 plus 360 times L minus 1 over N minus A. N is the number of poles, open loop. M is the number of zeros, open loop. And L is 0, 1 up to N minus M minus 1. Right? So if you have 2 asymptotes, L is 0 and L is 1 for the first asymptote, for the second asymptote. If you have more than that, right, you go 0 and 1 and 2 like that. Right, you substitute to this equation and calculate the angle. First asymptote, second asymptote, third asymptote, like that. Okay, fine. That is rule number 3. This is interesting. Angle of departure or angle of arrival. Now, let's say this is your pole plane and you have your open loop transfer function. You know your poles and you know your zeros. Okay. And let's say there's a pole or 0 here. Pole or 0 here, right? For the moment, let's say it's a pole. It's a pole. Okay. Open loop pole. And you know that this is the starting point. This is the starting point. one of the starting points. If you have, let's say, 3 open loop poles, you have 3 starting points. Actually, 3 curves. It's like 3 snakes. Okay. You start from here, one of the paths. And when you increase gain, it starts moving. It starts moving. We don't know the direction. So in order for us to be able to draw the locus, we need to know the angle of departure. Angle of departure. So from this open loop pole, where am I heading? Is it 0 degrees? In that case, it's over here. If it is 90 degrees, it's over here. It is 180, it's over here. 270, it's down here. What is that angle? And that is what is called angle of departure. So how do I calculate? And I have to calculate this for all the poles, open loop poles. In order to correctly find the direction of motion, okay, of these poles. So this is open loop pole, and this one on the root locus, it's a closed loop pole. It's a closed loop pole. So the closed loop pole starts from here and moves like that. Now, in order to understand this angle, what I do is I bring this point S, which is a closed loop pole, along this curve very close to the pole Pi, very close to the pole like this. Okay, very, very close. Now, if I'm here, if I calculate the phase S minus Pi, right, which is this angle, I will get this angle, S minus Pi. But as I get closer and closer to Pi, this angle becomes this angle. So when my S variable point is very close to Pi, this phase angle, S minus Pi angle, is actually the angle of departure, theta I. Can you see that? So can you see the point? If this arbitrary point on the root locus, if I move it very, very close to the pole, open loop pole, the starting point, and calculate S minus the pole angle, what I get is the angle of departure. And also, if you want to calculate angle of arrival, it has to be not a pole, but a 0, right? Then you get angle of arrival because it comes to that point. Here, it departs from the point, pole. So what I do is this. I know that I'm on the root locus all the time. So therefore, I satisfy the phase condition. I satisfy the phase condition. Total phase of GS is this one. Right? If I go back, I can show it to you. So here, angle KHSGS. Okay. So when HS equals 1, you can drop it. It is K times GS, total angle, but K is also doesn't contribute to phase. So therefore, it is angle of GS basically, right? Angle of GS. So angle of GS is 0 because is 180 degrees because we are on the root locus. And we are referring to a very specific point, S star, S star. What is S star? S star is S as S gets closer and closer to Pi. Okay. So very close to Pi, somewhere over here. So if you substitute that point to the root locus phase equation, it should satisfy the condition. So we write it like that. So this is angle of GS, S minus Z1, sorry, S star minus Z1, S star minus Z2, S star minus Zm. These are all zeros minus the poles. S star minus P1, S star minus P2, S star minus Pi. This is this one. This is this one. And you continue with other poles. Finally, S star minus Pn, the last pole. Right? All the faces from the zeros, all the faces from the poles, addition is plus or minus 180 degrees because we are on the root locus. So it has to satisfy the phase condition. Okay. Now, when S star is very, very close to Pi, this angle is angle of departure. This is angle of departure. For all the other ones, you substitute S star because it is very, 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 very close to Pi. You substitute Pi for S star, because they are very close. So you can say this is Pi minus Z1, Pi minus Z2, Pi minus Zm, Pi minus P1, Pi minus P2. Don't write here Pi minus Pi, then it becomes 0. But here what you say is this is angle of departure, theta I. And then continue until Pi minus Pn. Any questions up to that? This is very, very important point. Do you understand this last equation? Yes or no? Is it clear, the last equation? If it is not clear, tell me now, I can explain. Because you need to know this. You need to understand this, not just to remember. Any questions, or is it clear? Perfectly clear? Okay, I assume it is clear to everyone because there's no questions. Either yes or no. Dead quiet. So, yeah, we have 26 people in this class. Right, so because I don't know exactly whether you have understood this, I will just explain it one more time briefly. Right, this is the entire GS phase angle for S star point, which is a very, very close point to Pi, one of the poles. We want to calculate the departure angle from the pole. Departure angle is actually this S minus Pi angle as S approaches to Pi. So as S approaches to Pi, we give it a name S star, and S star is on the root locus. So therefore, it has to satisfy the phase condition. So this is the phase condition. All the zeros, all the poles with respect to S star, the phase has to be plus or minus 180 degrees. So when you write it down, A star goes to every term in the zeros and the poles. So therefore, what you do is you don't know what a star is by position coordinates, but you know it is very, very close to pi. So therefore, you can substitute a star with pi, except over here, where this S star minus pi total angle is actually the angle of departure. Okay. So this is after substitution. Pi minus Z1, Pi minus Z2, Pi minus Zm. Then the poles, Pi minus P1, Pi minus P2, Pi minus Pi. It is theta I, angle of departure. And then you continue with the same lines until you get the last open loop pole. And now, because these are all known, open loop pole, open loop zero, open loop pole, open loop zero. These are all open loop poles and zeros that you know upfront, so that you can calculate these angles. You can calculate these angles by different angles, and this is theta I. On the right hand side, plus or minus 180. Then you can calculate your angle of departure. So you can do this for all of the poles, open loop poles, right? And if you see, if you have a complex conjugate pole pair, you have to do that for only one pole, because you know it's a mirror image, right, with respect to the real axis. So what's happening above the real axis is happening below the real axis also in the mirror image. So that way you can figure out the angle of departure. It's heavily raining here also, and it's 4:30. Therefore, I will stop there for today. But wait a second. I can go through these two also today. Rule number 5, breakaway points. This is also interesting rule. I want to present without a proof. When two poles meet up at a point. Earlier you saw the two poles moving head on and meet up at a point, and after that they split, and one of the poles go north, the other goes south. So we want to find out at what is this meeting point and breakaway point. So meeting point is equal to breakaway point. How do I know that? If I know there is a meeting point, I use this equation, 1 over HSGS differentiated with respect to S equals to 0. Okay, so do that. Again, the proof can be found in undergrad books. Then you can calculate and find out where these poles meet up each other. Okay, and finally, as you know, some systems, when you increase gain, the poles cross over to the right half plane at some point, and that is where system becomes unstable. Remember the last time, when you reduce the gain, and one of the poles went to the right half plane, and the system becomes unstable. And there are some other control systems where when you increase gain, the poles cross over to the right half plane. So either way, we call it ultimate gain. So there is a simple technique to calculate what is this gain. If there is a maximum limit for the gain, and beyond that the system becomes unstable, how do you calculate that gain? And for that there is there's a simple method. We call it Routh-Hurwitz criterion, right? So that criterion we will understand, we will learn through an example. Okay, right. And finally, uh, let's say you have uh, your root locus like this. This is your root locus, and uh, you have a pole like this, one pole, another pole like that, right? That's all what you have. And as you know, when you increase your gain, this pole goes this way, this pole goes that way, and they meet up somewhere here, right? And after that, one pole goes up, the other one goes down, right? So you know that this is the root locus. And let's say at this point, you want to calculate your gain. What is the gain? What gain will bring my poles to this point, right? If you want to find out, okay, what is the gain I should set to get the pole to this location? So it is this equation. So this is the gain you want. This is equal to 1 over HSGS, S equals S star. So let's say this is my S star point. This is my S star point, right? S star, right? So if I know my S star, you put it over here. S equals S star, 1 over HSGS, right? You can calculate your gain. Simple. Right. So we learned these 7 rules today. Next time we will do an example. This is the example. If you want to give it a try at home, please do so. This is my open loop transfer function. My sensor is 1. This is the feedback gain. And you are supposed to draw the root locus, sketch the root locus. Okay, right. Any questions for today? Okay, if there are no questions, we'll stop for the day.
We say roots means all poles and zeros, right? When we consider roots.
No, when we say roots, it's basically poles. Zeros we don't consider very seriously, but they are there in the equation, so we have to treat them. But we are really considering the poles, pole locations, because the poles are the ones which characterize the behavior of the plant. And these poles, when you increase the gain too much, they reach the open loop zeros, right? So that is the last destination for some of the poles. Other than that, we are really concerned about the poles of the closed loop plant. And they start from the open loop poles and they end up at the open loop zeros. And right throughout, they have different characteristics for different gains. Any other questions? All right, then let's call the day off and I'll see you next week, right? And I'll put all the lectures and videos to the website within this week. Thank you very much, and I'll see you next week, right? Okay, bye.